All right, youngins, here we go. Let's do another optimization problem using derivatives. Now, I bet you've probably seen a problem just like this before, maybe back in Algebra 2 or something like that, maybe even back in geometry. But we're going to do it without a calculator. How about that? Woohoo! So, here we go. We've got a rectangular cake dish, which is being made from a rectangular piece of metal. We're cutting out some corners. Okay, each of the corners will be a square. And then we're going to fold those edges up along the edge here, right? These are going to fold up, which is then going to make us a little box. Okay, just like this, our cake dish. Okay, what we want to do is to be able to create a cake dish of maximum volume. Okay, so let's see what we end up with. Let's go ahead. We know that it's 25 centimeters along this side, and then it is 40 centimeters along this side. Now, it wants us to have the maximum volume. So, if we want the maximum volume, then what we're going to need to do is go ahead and find the volume in terms of what's being cut out. Now, we don't know the size of those pieces, so you should have done something like I said, like this before, where those pieces each have a size of x by x. But if I'm going to find the volume, let's go ahead. How wide or how long is this cake box going to be? Well, hopefully you see that that width is the same as this right here, which isn't 40 centimeters anymore because I've taken off x on this side and I've taken off x on that side because those are going to fold up to be the ends. And so that means that this length right here is going to be 40 minus 2x, one at each end. Okay? Now let's look at the depth here, or the whichever side you want to call this, the width, I guess. Okay? Now that is coming from this piece right here. All right? So that has a length no longer of 25 because I'm going to be taking off the 2x's there. So 25 minus 2x. Now the tricky part is, how deep is it? How thick is it right here? How deep is that pan? Well, that's coming from this right here, right? That's how deep your pan is going to be, how wide that x was. And so your depth is actually x. Now, how do we get the volume? How do we get the volume of that pan? Well, it's the length times the width times the height. And that will give us volume. All right? So, from that point, what we need to do is figure out how to get the maximum. Now, if you want, you can deal with it just like this. Most people, however, because they don't want to do the product rule twice, are going to go ahead and distribute this, and that's fine. So let's go ahead and do that, just for simplicity's sake. So 40 times 25. Well, 4 times 25 is 100, but it's 40, so that means it's going to be 1,000. 40 times minus 2x will be minus 40x. Then I got a minus 50x. And then, sorry, 40 times 2x, you probably got me there, is going to be 80x. 25 times 2x is 50, and then negative 2x times negative 2x is plus 4x squared. Yeah, you thought I was going to write it too, didn't you? Okay, and we still got the x on the outside. We can put those together to give us negative 130x. So now I'm going to distribute the x in there, and so I'm going to write it as 1,000x minus 130x squared plus 4x cubed, because this x has to distribute to everything in there. That's still equal to the volume. Now, if we're optimizing, if we're doing a maximum or minimum, then what we need to do is take the derivative. So let's go ahead and find the derivative of this. So put the 3 in, I'm going to go ahead and rewrite it in standard form. So I'm going to put the 3 in front. So that's 12x squared minus 260x, and then plus 1,000. All right, so that's what we've got. So at this point, we now want to find when the derivative is equal to 0. Now you've got a couple options here. Yes, you are more than welcome to use the quadratic formula or solving the square or whatever. I'm going to factor it though. So I know that I want the derivative to be equal to 0. So I'm going to go ahead and put that as being 0. So I see that everything here is actually divisible by 4. So I'm going to divide everything by 4. So 0 is going to be equal to 3x squared minus 4 into 26 would be 65 plus 250. And then I'm going to go ahead and factor this. Oh boy, what are you making me use my brain? Yes. Yes, I am. So 3x and x. Now, possible factors of 250, I guess it could be 10 and 25. But 25 times 3 is going to give me 75 and 10. So that doesn't quite work because I need the signs to be different. So I know I'm going to end up adding these two together. So it's got to be less than 75. Okay, well, we could try maybe 5 and 50. So let's try that. If we put 5 here and 50 there, then we've got a negative 50x and negative 15x. So that actually works, negative 65x. All right, so at this point we can now solve. And so we can set each one of these equal to 0. So x could be equal to 5 for this one. Or x could be equal to, add the 50, divide by 3. So 50 over 3. So it looks like both of those are possible options. All right, so let's go ahead and then do a sign diagram test and consider our options, because we want this to be a maximum volume. And so if we take the derivative and we put 5 here and we put 50 over 3 there, we go ahead and plug in a number. Let's put in 0 because that's easy. So if I put 0 in here and I put 0 in there, that's going to give me a positive. So that was going to be positive there, which means that this one is going to be negative, and this one is also going to be positive. Okay? And so that means positive, negative, negative, positive. Okay, yes, I'm working this one a little bit different than the last one, but that's the value of knowing everything about these, is that you can try it in different ways. This one is definitely a maximum. This one is a minimum. All right, now the other problem with this one right here is actually the fact that 50 over 3 is approximately 17. Now, that, remember, is x. That's the size of the hole you're cutting out the side. This side is only 25 long. You can't cut out 17 here and another 17 on the other side, because that adds up to 34. You only got 25 to work with. So that one actually won't work at all. It's got to be the 5. And a good thing that it's a maximum. Now, if we wanted to check that that's a maximum, we could do the second derivative. So I'm going to go ahead and do that. So I'm going to do a second derivative, which is going to end up giving me, I'm looking down at this one, so that's going to be 24x minus 260. And so then if I find my critical point where I get the inflection point, I'm going to make this 0. I'm going to add 260, so 260. Actually, I don't need to do that. I just need to factor. So, or solve. It doesn't really matter. But the fact of the matter is that when I do that, so 260 equals 24x divided by 24 divided by 24. So 260 divided by 24, I don't really know exactly what number that is. It doesn't really matter. It's pretty close to 10, which means it's somewhere around here. So when I put in my value, so if I put in, say, 0 for x, then that gives me a negative number, which means this part is concave down to the left of that, where 0 is, and this part is concave up, because this is the second derivative. This was the first derivative. And so concave down is what I want in order for me to be getting a maximum. So there you go. The dimension, that has to be the size of the square being cut out. We're done.